Recording in progress.
Sorry, I muted.
Madam, we didn't hear anything.
So I muted, no? Okay. Right, okay. We'll
About
start.
2 minutes, I think.
Okay, I will start again. Right. When, last day we discussed about the Einstein theory. Uh, we discussed the failure of the Newtonian mechanics. We are going to explain to some various phenomena and some experiments and observation of physics. We have discussed failure of the Newtonian mechanics. And also we replace the Galilean transformation with the Lorentz transformation. Now today, in session number 4, we have how the laws of Newtonian mechanics should be addressed according to the principle of relativity. Then last day we discussed about the length and time, I think you remember, and fundamental postulate, and investigate some velocity transformation also, right? And today we have to give the attention about energy and mass. Energy and mass, right? If then how the relativistic effect on mass. We discussed relativistic effect on mass in this session, right? The Newtonian definition of work, the mass of an object remain constant. We discussed like this. Can you hear me now, Nipuna? Nipuna?
Yes, madam, we can hear you now.
Okay. Then energy we'll discuss about in the Newtonian mechanics, work and energy, our famous topic. We discussed how the energy transfer to one energy to other one, and also increase in the kinetic energy, right? Then results of the increasing of the kinetic energy results in an increase in the speed only. I think you remember in level 3 and advanced level and also O level we discussed like this, right? But according to the Einstein theory, this is not happening. And we know P, kinetic energy equation is half mv squared, that you remember. Then when V is increasing, only V is increasing, kinetic energy increased. And that we take as the M as the constant. M as the constant, M is not varying. But in this session, we have to discuss how to vary M, mass of the object, according to their velocity, because we consider the objects in here, velocity is very much equal to the velocity of light. This is a relativistic speed, right? Then relativistic speed and the kinetic energy only increased by a small amount. Then we can see how the energy transferring and other things in this session, right? And momentum, then how the particle momentum can vary, we can discuss. And then how the mass of the particle is varying, we can discuss. Then Newtonian mechanics, the particle keeps picking up speed identically. In relativity, particle gains not the speed but the momentum, right? This can happen as the mass increase with the speed of the particle. The famous equation, I think you heard about this, E total is equal mc square. In Einstein deduced that the increased mass represents the increased energy. And they using the equation of special relativity, they derived an equation relating to the energy, mass, and the speed. Then E is E total energy is equal mass m c square. In your book, it is mentioned at the mc square. So I want to explain this. That's why I put as the mc square. Where mp can divide we can define ms over 1 minus c squared over c squared. Right? Then ms means rest mass and m means relativistic mass. In your book, it's mentioned as simple m. And here m naught. You can see page number 73, 4.2 equation. M equal m naught over 1 minus v squared c squared. So you can see this mass of the object is varied according to the velocity. Right? Here gamma. I think you remember this constant part is gamma. 1 over 1 minus v squared over c squared is the gamma. Right? Nipuna, can you hear me clearly? I can't increase volume. This
Yes,
is
we
my
can
max.
hear, madam, but there's
No.
not echo, but some unclear thing. I cannot explain it.
It seems like
We can
M
hear you loudly. But
With what?
we can hear you loudly, madam.
Okay, we see, right? Then this equation, then you can see total energy, total amount of the energy of moving object as written as observer. Then here you can see total value mc squared over 1 minus v squared. E total is the total energy of the moving object, right? M is the rest mass of the object. Then we normally we use this as the M naught. M naught is the rest mass, not any motion. It is in the rest. So mass of the object at that point we call this as the rest mass. Okay. Then v is the speed of the object with respect to an observer. We can take some speed of the object with reference to the references frame. Last day we discussed about the references frame and c is the speed of light, right? The speed of the object with respect to an observer we can take as v. So you can see mc squared over 1 minus c squared c squared. We call this as the gamma factor, Lorentz factor. I think you remember that, right? So in total we can write mc squared gamma m naught c squared. In your book, m is rest mass is mentioned as m naught. So in total we can write gamma m naught c squared, right? Then M naught is the rest mass. Then object is moving with velocity v according to the some frame of references. Then you can see mass is varying, right? If v is equal 0, then E equal mc square, right? M is the rest mass, then rest energy. E equal m naught c square. We call this as the rest energy. And this one is total energy of the moving object or relativistic energy, right? So the mass energy equivalence, this is the Einstein famous equation E equal mc square. It means that the rest mass of an object and its energy are equivalent. This energy is called the object's rest energy. The rest energy, E rest, is the amount of energy an object at rest as is respect to an observer, and it does not change, right? Respect to an observer, then you know observer, relativistic reference frames and other things. So famous equation is equal mc square. When rest mass of an object is and its energy are equivalent, then energy is called as the object rest energy. Right? E rest, we call this as E rest. The total amount of energy a stationary object as respect to an observer, then according to the observer, this object is at rest. So the total amount of energy we can write E rest equal mc squared, right? Total energy of the stationary object, right? This is the family example of this equation in the nuclear physics, right? It is very helpful to the nuclear physics. During the nuclear fusion, protons and neutrons combine in the interior of the sun to form helium nuclei, as well as the nuclei of the other elements. The difference in the masses of the reactants, the produce of fusion multiplied by c square equals the released energy. The released energy we can take by equal mc square. Then the famous equation we can take it, right? Then laws of the Newtonian mechanics and the principle of relativity. Then we can build up this equation considering by Newton's second law. Right? After discuss that, I will explain the board. Then the laws of Newtonian mechanics and the principle of equal relativity. You can follow your book, page number 73. This is slide related to the page number 73. Then Newton's law under the Lorentz transformation equations, we can build considering first law of the motions, we know that according to the Newton's first law, a body either remains at rest or in a uniform motion until it is acted upon the external force. I think you can remember this equation, right? This law is invariant under the Lorentz transformation also, right? If the body has a constant velocity in one inertial reference frame, then its velocities in any other inertial frame is also constant. Then according to the Newton's first law, does not need any modification as it an invariant under the Lorentz transformation. But then we consider in here Newton's second law because these are related to the particle mass and particle momentum and other things, right? So we can take Newton's second law. You can see this equation. This is related to the Newton's second law. I think you remember F equal ma, mass into accelerations, right? Then also you can remember we can replace acceleration by m into dv over dt because acceleration is rate of change of velocity. So equation can now replace by f equal simple m times dv over dt, and also m is constant according to the Newton's second law. And Newtonian mechanics, mass of the particle is constant, and we can take this as mv. mv means, mass into velocity. We can replace this by momentum. So if dp over dt, we can write d over dt mv. I think you got the idea in the equation 4.1. Here v is the speed of the particle of mass m, right? Now the equation 4.1, we is going to remain the assumptions that the m is the constant. Right? In the m is the constant, please turn off your videos. The equation 4.1, this is the written with the assumption of m is constant. But in the Einstein modified formula, we know m is equal m naught 1 minus c squared. I explained this, that m is identified as the inertial mass of the body and m naught is the rest mass of the body. That is at rest. M naught is rest mass, but then this frame is moving with velocity v. So we can replace simple m. Mass is m naught 1 minus c squared. Now we can introduce the formula 4.2 in equation 4.1. I think you got the idea, right? Then we can modify this formula 4.2 and when we can obtain in equation 4.1, because in here Newtonian m is the constant of the particle, but we know in the Einstein modifications m is not the constant value for all the time, and m is equal m naught over 1 minus c squared over c squared. M naught is the rest mass. Then we introduce the equation like this. F equal, you can see d over dt mv. Now we can write d over dt m naught 1 minus c squared into v. This is the equation, is the modified form of the Newton's second law, right? Now we can introduce about the W. We are going to build the mass energy equivalence. I will explain both after discussing this part, because in questions paper I am asking to prove the mass energy equivalence equations. Right? Normally I am giving how we build these equations questions, right? So you have to practice this, right? I will explain after that, right? This is the method, right? Then let W be the work done by the body in displacing it through a distance dr. Then you know how we find the work W. Distance is dr. The external force is F. So you know in the mechanically we can write W. Work is equal F dot dr we can integrate this some point to some point. So using the Newtonian second law, we can replace F by M du or dt. F equal ma. Ma means A means change of the velocity. So we can write M du over dt. I think you clear this. But here M is the mass and u is the velocity of the body in motion. Then by combine these two expressions, we can get W equal M. We can substitute M du or dt to F. M du or dt F dr. Let us write the equation in one-dimensional assumption along the x-axis. We consider it along the x-axis, right? So W is equal M dux over dt dx. I think you can understand this equation because du over dt we considering only x direction. So we can replace u by dux, right? And dr we can replace dx because displacement is changing on x direction. So I take changing the displacements at dx. So you can see this equation and dux over dt into dx. We can write this as dux times dx over dt. And the calculation is clear. Dx over dt, other things and dux, right? Right? Dx over dt we can take as dux like this, right? Work done on the body to change the speed u to u1 is equal half m u2 squared minus u1 squared. This is the classical mechanics because in this calculation we considering as mass m is constant, right? So this is the classical mechanics. We consider the kinetic energy of the particle of mass m moving with velocity v as the half mu square. The total work done on the body is equivalent to the change in the kinetic energy of the body. This is we know theory. Right? We know this theory, the classical mechanics, right? So here now let us derive the expression for the kinetic energy of the particle of mass m and relativistic motion. Here, then you have got this idea because after that we can introduce the other part. Here m is constant. This is the W equal half mu squared minus mu squared. Then in the classical mechanics, particle energy W is equal to the change in the kinetic energy. Now let us derive an expression for the kinetic energy of the particle m and relativistic motion. So you can write T equal F dx, d over dt mu dx, d over d mu dxt. Same thing. And but we know this is m and u are varying. M and u are varying. So this equation is related to the multiplication of integrations. Can you see? dmu dx over dt, this is the multiplication one because m also varying and u is varying, right? Then we can write this expression. Then I think you know the calculation. But first we take one is the constant and take the other integration part. M du. Another one we think u is the constant and m is varying. U dm and dx over dt is u. So you can multiply by u mu du and u square dm. This is the one each. The relativistic mass m of the particle is given by m equal m naught 1 minus u squared over 6. You have to practice this, okay? You have to practice this equation. So we can multiply both sides and take the cross multiplication. M squared u c squared minus m squared u squared equal m naught c squared. And again, I am going to differentiate this equation because I am going to build the relationship between 4.6 equation with 4.6. So we can differentiate this both sides. Here c is the constant, but m is varying, right? And u is also varying. So 2mc squared, we can differentiate this. dm. Another one is minus 2m u square dm and again minus 2m square u du because then m and u are varying according to the Einstein theory. That and this side m naught c square, m naught is the rest mass of the object. It is not, it is a constant because at that time rest mass is constant and c is the velocity of light, it also constant, right? M naught c squared part is constant. By differentiating, it may it become as the zero. Then you can see, we can take the one equation related to this the 4.6, right? Mu du plus u square dm. This is equal c square dm. Then you can substitute this value to equation 4.6. So we can obtain T equals C square dm equals C square dm m naught to m. Initial mass. Rest mass is m naught. And here u is 0. U is 0 means rest mass. It is at rest. Then mass is m naught. And velocity u, then now mass is m. Right? dm mc squared m naught c squared. Then we can take this as mc squared minus m naught c. Then you can see this equation. It is the uh, kinetic energy T. We take this as kinetic energy, but it is equal mc squared minus m naught squared. Relativistic energy and relativistic energy minus rest energy, right? Equation 4.7 shows you that the gain in the kinetic energy of the particle is the same as the change in the initial mass of the particle. This is the Einstein relativistic theory. Then equation 4.7 shows, gives the idea we again some kinetic energy of the particle is same as the change in initial mass of the particle. Right? This is the final mass mc squared, final relativistic mass and also initial relativistic mass. The difference between these two is equal to the gain in kinetic energy, right? Gain in kinetic energy. And also, we can write the kinetic energy T acquired by the particle to move with the speed u is given by this is mc squared. We know that m is the relativistic mass. It is equal gamma m naught c squared over gamma. If 1 minus v u squared c squared minus m naught c squared. This is the relativistic kinetic energy, right? And here T and this one is can compare total energy is equal T plus m naught c squared over 1 minus u squared. This is the E. E naught is equal m naught c squared, right? Particle energy can be written as like this, right? I want to explain some equation this way. I think you got the idea how we find the value of this one. The calculation part I need to explain. We'll give a questions and discussing.
Excuse me, madam.
Yes.
Will we need to derive this equation?
Yes, I will give one question. Please wait, right? I'm
Okay.
fine with this one.
Okay.
Then you can follow it. In kinetic energy, you can take this as T equal mc squared minus m naught d squared in this equation. You can start the derivation. I will give the equation from this one. I think this is clear for the kinetic energy. No need to explain again. Then after that, I am giving some question. Right? Up to now, you can solve this equation. I'm going to explain the relativistic momentum and some equation we have to derive. Then you remember this part, how we write the T, calculate m naught c squared 1 minus u squared. This means gamma m naught c squared minus m naught c squared. Then after that we can build the mass energy equivalence equation, right? Then after that, how we, so this, please wait. And this is very helpful equation for the spontaneous uh, breakdowns or something happen, the collisions. We have to find the some collisions and how what is the final velocity of after the collisions like this, right? You have to know this part. We can find the questions that we 2000 is right. Selalu. Giving a full scale. Mm. You can start available like this. I will stop this shortly. Can you see the board, Nipun?
Yes, madam, we can see.
Yes, ma'am.
Maybe this question is coming for the question number 6. Write down this one. Particle of mass m moves with velocity speed v. Question number 1. Particle of mass m moves with speed v. These are the information. Write down the relativistic expression for the mass m. For the mass m. In terms of its rest mass m naught. Rest mass is m naught, right? If the speed v and velocity of light c. Write down the particle of mass m moves with speed v. Write down the relativistic expression for the mass m. In terms of not only mass, we will write this down the relativistic expression for the mass m, and we can write here momentum and relativistic energy. Momentum and relativistic energy also. You can add this one, right? Energy. Right? First we look this one, right? We have to write down the expressions for this one, right? I think you have idea. M naught is the rest mass. Then the speed is v. Right? Then you have to write down the relativistic expression for its mass and also momentum and also total energy. Right? We will see this one first. Then we know relativistic mass, we can write gamma m naught. Okay? We call as the Newtonian mechanics. Relativistic mass m is equal gamma m naught. Then m is equal 1 over 1 minus v squared over c squared. This is the gamma factor into m naught. This is the relativistic mass, expression for the relativistic mass. And also you have to write m naught is the rest mass. Very clearly you can understand this, and please write clearly, right? If you face some questions, what is the relativistic mass? What's the relativistic momentum? What is the total energy? Like this, questions can ask. So clearly write down this. This is the mass. We know mass is varying with v, velocity of the particle. Name node is the rest mass. Okay. Then other one is asking the question, what is the relativistic momentum? Momentum we know is equal mass into velocity. Mass into velocity. Then now m is the mass. This is the relativistic mass. It is dependent on the gamma m naught. because this is moving with velocity v. So at the rest point, rest mass is m naught. In the velocity v, it is m gamma m naught. So you can replace this by p equal m naught v over 1 minus v squared over c squared. And also this is equal gamma m naught. This is the answer. This relativistic momentum. Very easy. Right? What's the expression for the relativistic momentum? You have to get the idea. Can you hear me, Nikita?
Yes, ma'am.
Okay.
Yes, madam, we can hear you.
All right. You have the idea about the mass. Mass is varying under the velocity. So gamma m naught v is the relativistic momentum. Then I ask what is the total energy? E is equal mc squared. This is the famous equation of the Einstein. So m is varying according to the velocity. So we can write E is equal m naught c squared over 1 minus v squared over c squared square root. Right? These are things you have to identify. Right? It's very easy. How we write the momentum related with the Newton's law, equation is same, but we know according to the relativity, m is varying according to its particle's velocity. Right? We can write relativistic part. Right? Can you understand? Right? Then other question, next one. This is the question is one question, then part A. Part A is right. Then next one. Using the relativistic expression. Next one. Using the relativistic expressions for mass show that the kinetic energy of the particle, the kinetic energy of the particle, kinetic energy of the particle, EK is given by EK is equal gamma minus 1 mc square. Right? The same meaning here. Then you have shown that EK mc square is equal gamma minus this one. Then how we write this equation? Right? Now we can write the last equation I explained in the PowerPoint slide. I will explain again, right? Then you can go to the idea. This is the question. Write down the question and then write the answer, okay? Then we can write and want to find the t value. What is the t? Want to see these equations, right? Gamma m naught c square minus gamma 1, right? Then you can write t. Kinetic energies we can write F dot du. According to the Newtonian mechanics, this is equal 0 to u, F dot du. And also we can write 0 to u, d over dt, mu du. Mu d, right? Dx, we take the x direction. We considering x direction. So you can write t is equal 0 to u, dmu into dx by dt. Into dx over dt, right? Then t we can write, according to this equation, m also vary, u also vary. Right? Multiplication here and integration sign here. So we can write 0 to u, this one m du. Within bracket, this is the constant and variation. And again, we consider u as the constant and m is the variation. And also dx over dt means the velocity of the x direction. We take this as the u. Right? Then t is equal 0 to u m u du plus u squared dm. U squared dm. This is the equation number 1. I discussed this in the PowerPoint, but I want to clear this one, right? Can you understand? Any questions? I think no, because these are the only integration and differentiation, dx by dt u. Then this is the multiplication, one take as the constant, other one vary. U is constant and m vary. Then we can multiply mu du plus u square dm. This is the equation number 1. Then I'm taking, this is my equation 1, m naught over 1 minus u squared over c squared. Right? And multiply both sides. Y squaring both sides. M naught squared. Here 1 minus u squared over c squared. And take the cross multiplication. M naught c squared. Okay, minus m squared u squared equal m naught c squared. Here m squared. M squared c squared equal this one. Right? Then take the differentiation because m vary, u vary, then c is constant. Then we can differentiate both the equation 2m c squared dm by differentiation. So m c squared dm minus 2m u squared dm minus 2m squared u du. Another side, m naught c square is the initial energy. So this is the constant. It's become as 0. Right? Then 2 cancel out. Mu du plus u squared dm. 2m cancel out, right? We can take the other side, c squared dm here, in other side, minus plus mu du plus u squared dm, right? Equal c squared dm. This is the equation. Equation number 2. I think now you remember equation number 1. Equation number 1 you remember. So both 1 and 2. This is the equation number 1. 0 to u mu du plus u squared dm. So we can substitute m du plus u squared dm as c squared dm. So I'm taking p as 0 to u c squared dm. Right? C squared dm. Okay. Then we know here limit is velocity, but now dm. And the velocity 0 means it's in rest value. So mass is rest mass. Right? And here u, velocity u, mass is m, relativistic mass. Right? We can change the limit as m naught and m c squared dm. So we can write this as mc squared minus m naught c squared. mc squared minus m naught c squared, right? Then we can write T also kinetic energy, Ek is equal mc squared. We can write gamma m naught c squared plus m naught c squared. This is equal m naught c squared into gamma minus. If you have the questions to prove this kinetic energy, you can take this. Okay. Then other questions, please write down this. The next one. This is the question, only one question and other parts, right? Next part is right. Then also we know kinetic energy we can prove like this. Ek is equal like this, right? Then next question is if P is momentum and E are the momentum and energy of the particle. And energy of the particle show that this is the another question. This is the mass energy equivalent equation. E squared equal P squared C squared plus M naught square C4. Then you have to know how to derive this equation. Very, very important. How to derive this equation, you have to know, right? E squared equal P square C square plus M naught C squared, right? Okay, now we will see how to derive this. Now we take the equation, next Ek value, right? Now we have to move with particle momentum and the total energy, right? You have to prove this, have to know how to prove this equation, right? Then energy equation we took Ek is equal gamma m naught c squared plus this one. So total energy we can write, total energy of the particle, we can write rest energy plus rest energy m naught c squared plus kinetic energy, the basic equation, right? Rest energy m naught c squared plus kinetic energy is equal total energy, right? Ek plus m naught c squared, and also we know E is equal gamma m naught c squared. Total energy we can write gamma m naught c squared, right? We take these two to build our equation, right? Then this can write gamma m naught c squared and Ek is equal this one. I'm writing this m naught c squared 1 minus v squared over c squared square root. U. We take this as u, right? Then kinetic energy I replace by T. T plus m naught c squared, because for my easy for the calculation, that's why I did this as T. T plus m naught c squared equal m naught c squared over 1 minus u square c squared. Now I am taking by squaring both sides. By squaring both sides. And taking the square value of the both sides, right? Then what happened? This is become m naught c squared square value over 1 minus u squared over c squared. Okay. Now you can multiply by cross multiplications. t plus m naught squared into 1 minus u squared c squared t plus m naught c squared value 1 minus u squared over c squared is equal m naught c squared. Right? Now, I want to take this u squared over c squared. U squared, I combine. Rearrange the equation. 1 minus m naught squared value divided by t plus m naught c squared. Can you understand this step? Right? M naught c squared now here. I want to take u squared c squared value. Can divide by t plus m naught squared. Divide by c squared and 1 value. Right? U squared c squared can write like this. Right? Please practice this question. Right? Question means how to derivation. Another one is t plus m naught c squared equal m naught c squared over 1 minus u squared c squared square root. Right now, this equation we can write as like this. You can see here gamma m naught value. Mass, relativistic mass. Right? I want to combine this with P, momentum. How we take the momentum value? I'm writing this equation as like this. Please check it is okay or not. PC squared over U. Like this, I'm writing this equation. P means gamma m naught U. C squared here and also we can divide U. Now you can see U cancel out gamma m naught C squared. Right? Equation is okay. Can you understand? I replace this one by PC squared over U because in given equation P here, then P we can write m gamma m naught U divided by U. So okay, then PC squared U, I replacing this by P. Now T plus m naught C squared U squared over C squared is equal P squared C squared by squaring or both sides and multiplying by cross multiplication. P plus m naught squared C squared U squared into C squared equal P squared C squared. And now you can rearrange the equation according to our equations, right? And you can rearrange this one. P squared C squared in other side. T plus m naught squared in here. We know E is this value is E. So we can write E squared over, we can write T plus m naught C squared value. I'm taking within brackets C squared right equation. E squared C squared.
And do we remember this whole step?
Yes. Okay, there is no any steps, then only calculation, right? Calculation part. A squared equals b squared, c squared equals. Yes, then one equation I think remember u squared over c squared equal 1 minus m naught c squared squared value t plus n naught c squared square. So you can multiply this pc squared u, it's okay. M naught c squared u will be okay. Um, yes, this equation can rearrange this one. T plus m naught c squared into squared minus m naught c squared is equal p squared c squared. Right, then we know t plus m naught c squared, the e squared value is minus m naught c squared. This is equal p squared c squared. This is our equation. We want to prove that a squared equal p squared c squared plus m naught c squared value. Here is squared value. No? Yes. Not easy. Then we can do like this, right? In page number 78 and page number 79, you can follow the equation E and P relativistic equation, right? The relationship between the total energy and the momentum of the particle moving with relativistic speed is given this equation. Then you have to know how to prove this, right? Right? Then the momentum of photon. Other thing is particle having rest mass 0, always moving with velocity of light. Right? Particle has rest mass 0, photon, like the photon, is moving with velocity of c. Then total energy, we cannot take as the equal mc squared because rest mass is 0, always moving with velocity c. We will see it like this. Momentum of photon, U. Then we know momentum P, mv is equal m naught v over 1 minus v squared over c squared. Square root momentum, right? M naught v like this. Then for a photon, for photons, we know traveling with v equals c. V equals c. It is close to the velocity of light. V equals c. So we can write rest mass m naught is equal P m naught v. Then we can write this as m naught equal P over V times 1 minus V squared over C squared half. 1 minus V squared over V squared. The photon with velocity V equals C. The rest mass we can write M naught is equal P by C into 1 minus C squared over C squared half. Right? Then you can see is equal 0. Then you can do that E equal M naught C square also rest energy is 0. Energy is 0. Then we can tell that rest energy of the photon is 0. Right? Rest energy of the photon is 0. Then how we write the energy of the photon? Rest energy is 0. We can show that. And also photon moving with velocity c and its total energy E. P we can write mv and also mc and mc squared over c. Right? mc we can write mc squared over E is equal E by c. Also the energy of a photon in terms of its frequency nu. Frequency nu is given by E equal h nu. We can write energy of the photon E equal h nu. Nu is the frequency of the energy, right? What is the h? H is the Planck constant. Which is the Planck constant. H is the Planck constant. So we can write E equal h nu. Then C equal nu lambda. V equal F lambda equation. For the photon, we can write C equal nu lambda. Then we can replace this E equal hc over lambda. Right? And P is equal h over lambda. Momentum of for the given value of lambda, the photon has the finite linear momentum. Is equal h over lambda. So sometimes they will ask how to find the momentum of the photon. Then you can follow these steps. P equal mv, mc squared E over c. And also E we can write h nu, which is the Planck constant, and c h nu over lambda. Then sometimes they can ask the question and sometimes ask how we calculate the relativistic mass of the photon of wavelength 12,000. Then momentum can write like this. P equal h over lambda. Then after that they will ask a question like this. Calculate the relativistic mass of the photon of wavelength 5,000 angstrom. Right? Then we can write, we know P equal h lambda, we prove that. And also we know P equal mv for the photon with velocity c. The relativistic mass of the photon m is equal h over lambda into 1 over c. We can write like this. Over lambda m or mv, p equal mv. Then mv can write p over b. P is h over lambda. Then velocity is c. So p over c. And we can substitute for the p. H over lambda is 1 over c. Now we know h. H is the Planck constant. 6.62 into 10 to the power minus 34. And c 3 into 10 and lambda is given 5010 into 10 angstrom. Then we can find relativistic mass. By substituting all the things, we can find the relativistic mass. Okay. Then the next problem is then this is the related to the relativistic energy and photon energy like this, right? Then we can find energy of some particles by after the collisions. What is the particle energy like this? I will discuss that one by example. Please with me. Questions. Sometimes the particles can break with for this equation also we can apply energy conservation law also. And momentum conservation law we can apply. I'm finding some question, please. Let's see.
Madam, excuse me.
Yes, Vandana.
Madam, when we consider the energy of a photon, how we ended up that E equals HF equation? I mean, what is the path? Just a curious question.
P equal H over in this one.
No, I mean E equals HF. How we ended up with that equation? What is the path?
E equal H nu one.
Yeah, equals H nu. Oh, yeah.
Then for the radiation, we know the equation, right?
Yeah.
E
How
equal
we
H
ended up
HF,
that
right?
equation? So, yes, madam.
E equal H nu, we know the equation, right? For
Yeah,
the
we know the
radiation,
equation. Yeah, my question is how we ended up that equation. What is the path of differentiation or anything?
no differentiation. The last question you asked,
No,
for the
no,
last question?
not about the question, madam. I'm asking about the theory part. E equals h nu.
Yes. H nu is the we know this equation.
Yeah, we know that equation.
Yes.
Madam, අපි equations දැන් මේ derive කරලා ගන්නවනේ. මේක එන විදිහක් ගැන කතා වෙන්නේ නැති තමයි. madam,
Speed වැඩි වෙලා ඇහෙන්නේ.
madam අනික් equations දැන් අපි prove කරන විදිහක් ගැන කතා වෙනවනේ. E සමානයි h nu එක කොහොමද ආවේ එතෙන්ට කියන එක ගැන.
H nu එක ඒ quantum mechanics වලදී තියෙන්නේ. ඒ කියන්නේ ඒක අපි එතෙන්ට use කරනවා. ඒකට අපි එතෙන්ට prove කරන්නේ නැහැ ඒක. ඒක ගන්න පුළුවන්.
හරි madam. ඒක අපි පාත් එකක් අපිට අවශ්‍ය වෙන්නේ නැද්ද කියලා දැනගන්න ඇහුවේ.
නෑ.
okay madam.
ඒ කියන්නේ radiation එකක ගන්නවා. This equation you can use some cases like I will some question. Okay, no problem. We will see the PowerPoint later. Other parties. Can you do the extra day school on? When we start the CAT exams, I want to discuss other part and also discuss the questions.
It start on 2nd, 8th February.
Next, tomorrow I have another lecture for the special degree student. Can you do one lecture on 24, Nipuna? This Friday,
Which school the madam?
I
The
will
night
available
day.
at 8 o'clock.
Yes, madam, we can.
We are having
night day school එකනේ
practical.
madam.
Ah,
රෑ 8ටනේ.
The night day school madam.
night day school එක මේ schedule කරපු එක දැම්ම නෑනේ මට extra එකක් කරගන්න.
ඔය ඒක තමයි madam මේක අපේ extra එක රෑට දාන්න රෑ 8ට වල.
ඔව්
Also
රෑට
night.
කමක් නැහැ madam.
මට ඉවර කරන්න බෑ මම තා චුට්ටක නතර කරන්නේ.
4නේ madam.
24th we can do, ma'am.
It's okay. Visitor cameras. Assignments එකක් තියෙනවා එක. තව assignment එකක් submit කරන්න. තව පොඩි part එකක් කරන්න තියෙනවා Doppler effect එක. පුළුවන්ද?
No issue madam.
Okay. මම එහෙනම් මෙතනින් නතර කරන්නම් අද.